Um, so a new technique for problems involving rolling or sliding along surfaces. Okay, so if you have a problem like um, you have a surface like this at an angle, and you have a box here and a box here, and a force is applied like this. The new thing that we're going to do is choose a coordinate system uh, with the y-axis pointing directly out of the surface and the x-axis parallel to the surface. Yep, yep, that's right. Okay, so in this example, then the y-axis would be straight out like that. The x-axis has to be this direction then, otherwise it's a flipped, not just a rotated version of our usual coordinate system. Okay, and let's think about what the benefits are and what the costs are of doing this. So why are we going to do this? We're going to do this every time from now on that we have a rolling sliding problem. Notice that if the thing is rolling or sliding along a horizontal surface, then we've been doing it all along because the y-axis points up straight out of the surface. But why do we want to do this in cases um, where the surface isn't horizontal? Okay, so to answer that, let's just think about what the benefits are and the costs. And it's not going to be worth doing if we have more cost than benefit, you know. So okay, what are some of the benefits? The first one is that the acceleration vector. Notice that if something's sliding or rolling along a surface, it can only move parallel to the surface. Okay, so the acceleration vector will always be a0. Then you have to calculate what the value of a is. But look at this. So what if we use the usual coordinate system here? These objects can move along this diagonal line along that surface. And so that would have an x component and a y component. You'd have to use cosine and sine to figure out what it is. It would just be a pain. Okay. So by turning the coordinate system, we get a really easy representation of the acceleration. The second benefit is that the normal force that's applied to the object from the surface will always be 0n. That benefit is basically the same as the one with the acceleration. So that normal force is perpendicular to the surface. If we use a standard coordinate system like that, We'd have to use cosine and sine to represent that normal force. Not just a pain because you have to represent it, but also because you have an unknown then multiple. You'd have like n times this cosine and sine thing, and it would make solving the equations more complicated. You have to solve everything as a system of equations. So these are pretty big benefits. And then there's one other one that comes up pretty often, and that's any force that's horizontal or vertical, and those are both pretty common. Are represented with a single component, repped with one component. I guess, yeah, that's bad wording. Yeah, thanks. That are parallel, perpendicular. Or perpendicular to the surface. That's better. And this is common. Those come up a lot. They're represented with a single component. Okay, so that's three big benefits. There is one cost too, but the benefits heavily outweigh the cost. But here's the thing that gets worse in this rotated coordinate system. Up until now, the weight force has always been really easy to deal with. It's always just been in the negative y direction. So 0, negative mg, that's always been the weight force. But now, in this rotated coordinate system, if the weight force is going down like this, now we have to represent that vector in a coordinate system at a funky angle. And so we have to use cosine and sine to represent the weight force. And so for each individual problem, we're going to have to calculate some angle, figure out some angle for the weight force. That's sort of a pain, but it doesn't undo all the good stuff that happens. And that's why overall, we're going to be better off with this rotated coordinate system. So the weight always gets more complicated. And notice that, so the weight is equal to mg, whatever that is, the magnitude, times the cosine and sine of some angle. And we're going to have to figure out what that angle is. So I'm going to spend the rest of the class just doing different examples with this. So let's start with an easier one. So let's say that this angle is 10 degrees. And let's say we have a cart on the incline. And the cart has a mass of, well, it turns out it doesn't matter what the mass is, but let's say it's 5 kilograms. What's the acceleration vector for the cart? That's a good question. It turns out that it doesn't matter whether it's going up or down. So say that it's at rest. Okay? We're going to go through all these equations and calculate which way it's accelerating. And that says, that'll say that it's going to start moving down the ramp at a certain acceleration. Okay. Now let's say that it's already moving down the ramp, okay, 2 miles per hour or whatever. Then the thing that we calculate is still going to be the acceleration down, which means it's going to tell us how much this is going to be speeding up. Okay. Now say it's rolling up the ramp and we do this calculation. We get the same answer, and since the velocity is this way and the acceleration is this way, that acceleration tells us how much this is slowing down. So the answers that we're going to get have no dependence at all on the velocity. Although I should say that when we start talking about friction, that's going to change. But that's why for now, I'm never going to even tell you where it's going, because nothing would change if it's going up or down or whatever. As far as the acceleration, the interpretation would change. Okay, so free body diagram of the cart. 5-kilogram cart. The coordinate system we're going to use is like this, with the y-axis out and the x-axis along the surface. There's a downward force of gravity. That's 5 times 9.81, so 49.05. And then go around the boundary looking for contact. The only place where there's contact is at the wheels. So that's a pushing force. I'll call that N. Now, we know we're going to, in this rotated coordinate system, we're going to have to come up with components for that 49.05 Newton force. So let's do that before I even go to Newton's second law. So here's the coordinate system. And the weight force is straight down with a magnitude of 49.05. And in any problem where the angle that's given is an angle from the horizontal to the incline, okay? The angle that's given then is going to be the angle between the negative y-axis and the weight force. And I can sort of maybe explain how that works. If you think of like the green as the x-axis and the red as the y-axis and the pencil is the negative y-axis. Okay, so I'm going to first start with an unrotated coordinate system. And in that case, the weight force just goes right along the negative y-axis. Okay, and then how far do I have to rotate this thing to make it match up with this coordinate system? 10 degrees. So I'm going to rotate this whole coordinate system, including that negative y-axis, 10 degrees this way. And now what you have is a 10-degree difference between the weight force and the negative y-axis. Okay. What we want to represent this in terms of cosine and sine is we want to know the counterclockwise angle from our x-axis to the weight force. So we want this angle. This one is 10 degrees. So what's our theta going to be in this case? 260, yep. If you went all the way around back to the green line, it would be 270, right? 90, 90, 90. But we fell 10 degrees short of getting there, so 260. And so that weight force is 49.05 times the cosine of 260 49.05 times the sine of 260. So that's, can someone calculate that for me? Okay. Okay. And does it make sense that both of those are negative? Yeah, because between here and here is the third quadrant, so those both have to be negative. It's going to take a little practice probably for most of you haven't done a lot of stuff with rotated coordinate systems, so it's going to take a little while to get used to not thinking about there being like a true coordinate system. But whatever we say is the coordinate system, that's the coordinate system. And that says this is the first quadrant, second, third, fourth, and we don't care about what the usual coordinate system says. Okay. Remember that when you're doing this stuff, the calculations that we're doing with that weight force vector are identical to calculations that you did in the vector practice problems. So if you get confused about this stuff, you might want to look back at that and remind yourself. Okay, it's been a little while now, but that's what we're doing here. Okay, so now that we have that, we can go to Newton's second law. And Newton's second law says, so what forces do we have? The normal force is easy. That's always 0n. And then we have the weight force that we just figured out is negative 8.517, negative 48.305. And that's equal to the mass of 5 times the acceleration, which I said is always going to be a0, so that's easy. What are we trying to find here? We're trying to find a, and you can see, so this here is the acceleration vector. It's just not complete until we know what that variable a is. So to find that variable a, we only care about the x equation here, so I'm not even going to do the y equation. The x equation says 0 minus 8.517 is equal to 5a. So can someone divide that? What's a? Negative 1.73. Oh, 703. If you plug that back into the vector to get the acceleration vector, you get that the acceleration is negative 1.7030 meters per second squared. Or if you want to think about it as a magnitude and a direction, this is negative x direction. Our negative x direction is down the incline. If you look back at our picture. Okay. And so this would be a magnitude of 1.703 in this direction. Any questions about that? Okay, so now let's say that we have a ramp. Which way was this one going? So now let's say we have a ramp going the other way. Let's say that angle's 30 degrees. And we have two carts in contact. Let's say that's 1 kilogram, and that's 2 kilograms. And then there's a force pushing up at, let's say this is 20 newtons. And let's say we want to calculate two things. First, what's the acceleration? And second, what's the force on the 1 kilogram by the 2 kilogram? Okay, well, part A asks for the acceleration. Do we want the acceleration of the 1 kilogram or the 2 kilogram? That's the same. They're moving as a single thing. So what are we going to isolate to calculate the acceleration? Remember that? So anytime you have a problem like this where things are moving as a single unit and you're trying to, and you don't know the acceleration, the first thing is to isolate the whole system together and calculate the acceleration. And here's why that is. So let's say that we first, we see eventually we're going to want a force on the 1 kilogram. So let's say right from the start, we just isolate the 1 kilogram. So we're going to have a bunch of stuff going on, but the unknowns that we're going to have in the x direction along the surface are going to be an acceleration. It's going to be a variable a. There's also going to be a pushing contact from the 2 kilogram, and we don't know what the magnitude of that is. Okay. So we're going to have one equation, the x equation from Newton's second law, with two variables in it. And at that point, you can't solve it, which means we're going to have to isolate something else and solve it as a system of equations. It's easier if you isolate the whole thing and you can calculate the acceleration right off the start, right off the bat, and then isolate something else and you already have the acceleration. So if you don't know the acceleration, the first step is pretty much always isolate the whole system and calculate the acceleration. Okay, so the coordinate system looks like this. The y-axis pointing out of the surface. The x-axis is down the incline. Free body diagram of both parts together. We have a weight force acting down. What's the magnitude of the weight force? Yep. So it's 3 kilograms times 9.81, 29.43. And then we have this 20 Newton force applied over here. And where else are the surroundings touching the? Yep, so there's a pushing contact from the ground. I'll call that N total. And before I go to Newton's second law, I'm going to calculate the angle for that weight force and come up with the components. There's X, there's Y. The weight force is straight down with a magnitude of 29.43. This 30-degree angle here means that this is 30 degrees. The angle we want is from the positive x-axis to the vector. So what's theta in this case? 300. So notice that in the last problem, our angle theta was 270 minus the 10 degrees. In this case, it's 270 plus the 30 degrees. And that just has to do with which way the ramp is flipped compared to horizontal. And so as components, we have 29.43 times cosine of 300, 29.43 times the sine of 300. And what do you get for that? Can someone calculate that? 0.715. Thanks. So then Newton's second law says 0 n total plus the weight force, 14.715, negative 25.487. And then this 20 Newton force, what's that? Yep, that's in the negative x direction, so that's just negative 20, 0. That's all the forces, and those add up to equal the mass of the system times the acceleration vector of the system. Now all we have to do is calculate that variable a. So there's the acceleration vector. We just need the variable a. So the x equation says 0 plus 14.715 minus 20 is equal to 3a. And so negative 5.285 is equal to 3a. And so what's a? Negative 3 point what? 3 was just an approximation. Sorry, 1.76. Okay. Meters per second squared. And so as an acceleration vector, plug that a value into the acceleration vector, and you get negative 1.760. The negative x-axis is, in this case, up the ramp. And so you can think of this as going up the ramp with a magnitude 1.76 meters per second squared. Because the positive x-axis is this way, and the force is in the negative x direction. And so what this acceleration says, just to elaborate, sort of mention again what I said before, nothing that's come into any of these equations has asked anything about the velocity. The velocity didn't matter for any of this. But now, how we interpret this might be different depending on what the velocity is. We know that it's accelerating up the ramp. So that means if at this instant that we're analyzing, the cart was already rolling up the ramp, that that means that it's going to speed up. The acceleration and velocity are in the same direction. It's going to speed up going up the ramp. If it's at this instant on the way down and the velocity is in the positive x direction, then it's going to slow down because the acceleration and velocity have opposite directions. If at this instant it has no velocity, it's at rest, then it's going to start to accelerate, start to move up the ramp. Okay, so now we want to calculate, we have the acceleration, we want to calculate the force on the 1 kilogram box by the 2 kilogram box. We want to isolate. Yeah, let's isolate the 1 kilogram because we're trying to calculate a force on that. So free body diagram of the 1. Okay, so we have a downward force of gravity, and the magnitude of that is 1 times 9.81, so 9.81 newtons. And then that 20 Newton force is acting on the boundary of the 1 kilogram. And so we have to put that in there. So that's 20. And now if I keep going around the boundary in this direction, the next place there's contact is where the 2 touches the 1. That's a pushing contact. So what direction is that force going to be? Down the ramp or up the ramp? Yep, it has to be toward the chosen object. So there's a force there, and I'll call that capital R for reaction, but you know, that's just a variable. And then the last place is where the wheels touch the ground. There's a pushing contact from the ground, and I'll call that N1, the normal force on the 1. We will all the time when we start dealing with friction. And you would use that normal force if, so the only reason we didn't use it in either of these 2 examples so far is because I didn't ask for it, you know. If you worked for a company that made wheels for cars that rolled on 10-degree inclines, it probably wouldn't have a very successful company, but maybe that's what you do. And then you would want to know what that normal force is because that's the force that the ground is applying to the wheels, and that's what the wheels would have to be able to withstand. Same thing, you know, if you built the ramp that it was rolling along, that's the magnitude of the force the wheels are going to apply to the surface. So yes, there are times you would want to use that. I just haven't been asking for it. So the normal force will not because of the rotated coordinate system. Okay, so Newton's second law. I don't have to go through the thing about thinking about the angle again because the angles for all the weight forces are going to be the same if you're in the same coordinate system. So that's going to be 9.81 times cosine and sine of 300 degrees. So if I put these all into Newton's second law, that R is in the positive x direction, so R0. The 20 is in the negative x direction, so negative 20, 0. The normal is always 0, n, and 1 in this case. Yes, that's right. And then the weight force is 9.81 times cosine and sine of 300. Can someone calculate that for me? That's in radians, I'll bet. Yeah, positive 4.905.496. And then that's equal to the mass of 1 times the acceleration vector, which we calculated in part A. So that's yeah, this is the weight of this object, 9.81 times the cosine and sine of 300 degrees. And so the x equation says r minus 20 plus 0 plus 4.905 is equal to negative 1.76. And so r is equal to, can someone calculate that? 13.3 repeating newtons. And to put that into a force vector, this here is the force vector applied to the 1 by the 2. We just didn't know what r was yet. So plug this value in for r, and you get that the force on the 1 by the 2 is equal to 13.3 repeating 0. Or in other words, it's this direction with a magnitude of 13.3 repeating newtons. Any questions about that? Okay, so now let's do a part C. And I want you to isolate the 2 kilogram part and calculate what's the force vector on the 2 by the 1. Anybody know what the answer is going to be? Yeah, it's going to be the same magnitude as this force in the opposite direction. And so what I want you to do now is draw a free body diagram, go through Newton's second law, and see if you can see how that calculation works. It should give you that exact same answer. Okay? And talk to each other, compare your answers to each other as you go. Ask me questions if you get stuck. And then after you have a little time to do it, I'll do it up here. Okay? So now we have a free body diagram of the 2 kilogram cart. There's a weight force down of 19.62. There's a pushing force up from the ground. I'll call that N2. And over on the right side, that's where it makes contact with the 1 kilogram cart. That's a pushing contact, so it has to be toward the chosen body. And I'll call that R again. We're going to see that it has the same value when we do the calculation. And if you look at the whole picture again, there are no other forces on this. So this is a complete free body diagram. Anybody have any questions about that? Okay, so Newton's second law says 0 n2 plus negative r0 plus this weight force, which is 9.81, 16.99. And that's equal to the mass of the chosen body times the acceleration vector, negative 1.760. And the x equation says 0 minus r plus 9.81 is equal to negative 3.52. Yeah, R is going to be, so these R values are always going to be positive because we always know the direction of the force going into it. I guess the best way to think about it is you put a negative in because if you go back to, this is the force vector on the 2 by the 1. And so if you plug a positive value in for R, you get a vector in the negative x direction. So what do you get for this? Hopefully it's the same. If it's not, it's just round off air. But okay. I'm going to say it's the same. And so the force on the 2 by the 1, plug that 13.3 repeating back into this force vector. That's that one with the dotted red line is the force on the 2 by the 1. And you get negative 13.3 repeating 0, or in other words, a force going this way with a magnitude of 13.3 repeating. So look at, this is something sort of interesting about this. Puzzle on this one for a while. So when we isolated the 1 kilogram, there was a 20 Newton force in it, right? And if there wasn't that 20 Newton force there, it would drastically change the contact force between these two objects. In fact, if there wasn't that there wouldn't be any contact force between them. But now when we isolate the 2 kilogram cart, so we know intuitively that that 20 Newton force is important for how this contact force works. But our free body diagram from our 2 kilogram, it doesn't even look like it knows that that 20 Newton force is there. So how is it? It's like magic. Like how does how do the equations for the 2 kilogram part know about that 20 Newton force? Like how can it be the same if this one doesn't have it in there? Exactly. Yep. It does know about that 20 Newton force because before we did this part, we'd already calculated the acceleration on the system. And that acceleration came about because of that 20 Newton force. So that 20 Newton force, it doesn't show up as a force, but it's built into the acceleration part. Okay. And it's pretty cool how it works, isn't it? I like that.
And then when you isolate the 2 kilogram part, you're basically just pushing through the
Mhm.
kilogram so that
Yeah, right. Although, you know, really, I don't like that way of thinking about it too much because I think like it kind of messes up the nice simplicity of thinking about what forces are acting on a body, you know? Like, so when we isolate this 2 kilogram part, and I think this will help you like not make mistakes to think about it this way. Like, what forces are acting? Don't think about like that. Don't think about the fact that that 20 is like pushing through. You know what I mean? I would recommend the way you think about it is just like, well, we know there's a weight force, and now we're just going to look for the contact points with the surroundings. There's one there. There's one there. As far as we know, isolating this thing, there's no such thing as that 20 Newton force. Put it into the equations and it'll all work out that way. But sort of thinking about it like kind of loosely, intuitively, you're right. I guess that is right. You're right. That is what it's doing. Yeah, you're right. That's funny. Yeah. I'm sure you could come up with examples with like complicated stuff going on where, but that is what's happening in this case. But what I'm trying to say is don't do that. Just think about the weight force and then go around the boundary and put in the contact. And if you do that, it's kind of hard to screw it up, you know. But if you don't do that, it's very, very, very easy to screw it up. Okay, let's do one more. So sort of a similar one. Actually, let me do this one. So I was going to give sort of a simpler one that you could work on, but I'm going to do sort of a more complicated one. We've done one a lot like this, but think about this now. And this is one that's going to come up in lab, hopefully, if we have enough labs left. So let's say we have a cart rolling on an incline. Let's say this has a mass of 1 kilogram. And it's connected to a cable that goes over this pulley. And then on the other side of the pulley is this 0.5 kilogram mass. And we want to know what are the cable tension and the acceleration of the 1 kilogram part. And we need to choose an angle here. Let's say this is, I'm going to use 30 degrees because then I can use the trigonometry we already did. Okay, so remember, we did a problem like this, I think, last class, except that there was no incline there, that was just horizontal. Right? We did one like that, didn't we? And so this mass, no matter what it is, if this is horizontal, this makes the system accelerate that way and that way. Now it's a little hard to tell. I'm not exactly sure what's going to happen. We'll find out.
Getting all mixed up on the directions, but it seems like if you just let that go, it could be going down.
It could be, but if you made this a little heavier, it would roll this way, you know? So I'm not really sure what the numbers. Right, right, you cannot. Um, because, you know, with any pair of weights, you could find an angle where it would be exactly zero acceleration. Actually, I'm looking at this right now because I'm thinking I might have actually chosen an angle where it's going to be zero. So let's not do that because that's boring. Okay, so let's make that 20 degrees. And so what we're going to do is when we analyze the 1 kilogram cart, we're going to use a rotated coordinate system. When we analyze the half kilogram cart, we're going to use mass. We're going to use a normal coordinate system. It's fine for those two to be different. And then now, besides that, we're going to go through this exactly the same way as we did when that was a horizontal, when that thing was rolling along a horizontal surface. So that means I'm going to isolate this one first. I'm going to come up with an equation that has two variables in it, so we can't solve it. Then I'm going to isolate this one, come up with an equation that has the same two variables, and then we'll use those two equations to solve for the two variables. If you go back and like later and compare what I'm doing here to what I did last time, you'll see everything's just the same except for the fact that there's that angle there, so the weight force is. Okay, so first I'll do a free body diagram of the 1 kilogram cart. No, right. Some people do that, but it's kind of like and like it can get you the right. I just don't like it because you're skipping a lot of stuff. Like, because if you wanted those to be part of a single body, you'd also have to include the cable. And then there's forces on the cable from the pulley, and we don't have any way of calculating that. So, there is sort of a shortcut way that works, but I don't like it. Yeah. But if you talk to, other people tell you to do it a different way. Yeah. Right. Okay, so we have a downward weight force of 9.81. We have the normal force from the ground, and then we have a cable tension, because that's a pulling force away from the chosen body. And that weight force is negative 4.905. Oh, that's right. Okay, so there's the weight force. This angle is 20 degrees. The angle we want is this, and so it's 270 minus 20 degrees, so 250. And so it's 9.81 times cosine and sine of 250 degrees. Can someone calculate that? Okay, so Newton's second law says negative 3.355, negative 9.218 plus 0n plus positive t0, that's in the positive x direction, is equal to the mass of this body, 1, times the acceleration, a0. And so now I'm going to use the x equation, and it says negative 3.355 plus 0 plus t is equal to a. And I'll rewrite that as t is equal to a plus e.355. And we can't solve that because that's one equation for two variables. So I'm just going to set that aside as equation star. And we'll come back later and use that in our system of equations. Any questions about that? And now I'll do a free body diagram of the hanging mass. There's a weight force of 4.905. The cable's pulling up on it, so we have that same force T, but up. And remember, for this body, we're using the normal coordinate system, so we don't have to deal with the angles and stuff. So Newton's second law here says negative 4.905 plus 0t is equal to the mass times the acceleration. And this is the last trick in these kind of problems. So now we have to think about the relationship between motion of this object and motion of this object. Okay. So we said that the acceleration of this one, sort of by default, if A comes out positive, is in the positive x direction. Okay. So if you move this 1 inch in the positive x direction, where does this go in its coordinate system? Yeah, it goes 1 inch in the negative y direction. So if we're calling this acceleration a0, we have to call this one 0, negative a. Okay. So this is 0, negative a. And now the y equation says negative 4.905 plus t is equal to negative 0.5a. I'm going to call that equation 2 star. And now equation star and equation 2 star are two equations for the same two variables. So we can substitute this expression for t into equation 2 star. I'm going to sub equation star into 2 star. And we get negative 4.905 plus the quantity a plus 3.355 is equal to negative 0.5a. So all I did here was where the t was in equation 2 star, I put in the stuff that we learned t is equal to from equation 1 star. I just substituted in. And so that says that A, well, let's see, I'm going to move all the A's over to the left. So we have 1.5A is equal to, can someone, what's 4.905 minus 3.355? 1.55. And so A is equal to 1.03. I think I've seen these numbers before. Meters per second squared. Is it going up or down the incline? It's going up the incline because if you plug 1.03 for A into this acceleration vector, it's moving in the positive x direction. So up the incline, and the hanging mass is accelerating down. And then what about the cable tension? Well, so now we can plug A into equation star. And you get that tension is equal to 1.03 plus 3.355 is equal to 4.385. Significant figure disasters everywhere. And so if this is the application you want to use that cable for, and you have a cable that can only withstand 4 newtons of force, then it'll break, And that's the kind of thing that engineers would use this sort of analysis for. 4 newtons is about 1 pound. So that's not a lot of force, but. Any questions? Okay. See you Thursday. Oh, what? That's T. Oh, so the acceleration is, plug that into the acceleration vector for the 1 kilogram one here. And so you get, where is it? 1 point, okay, so the acceleration of the 1 kilogram is 1.030. Oh yeah, it is. Yep. And if you plug 1.3 into the equation for that one, that's what you get. Yep. It has to be, unless that string stretches or something, but we always assume it doesn't.